Good evening. How are you all? Good. How was the first week? Long. Just get longer. So we need to finish what we started on Wednesday. Take a few minutes. Start with Neo. What did we talk about last Wednesday? What, digital? Why we use digital computers? Numbers? Why we actually learn? Why do we have to learn binary? Some arithmetic operation, negative numbers. Any question on that? No? Let's do a quiz. Just kidding. But I'll have a homework on that because I think it's important to know and see how it works. Cool? So, why powers of 2? Can you answer this question? If you have 8 bits, how many possible combinations of values can you represent? 2 to the power of 8. Why? Binary. 1 bit, how many combinations? 2. 2 bits times 2. 3 bits times 2. Does that make sense? And you will see this pattern a lot because we use binary. So what if you don't have enough bits to represent your value? Is this possible? How so? Can you give me an example of when this happens?
If you're in 2's complement notation, it basically cuts it in half. So if it's unsigned, you've got from 0 to 254, but if it's 2's complement, yeah, 55. That's, if you're using 2's complement, you've just got half of that positive and then half negative. So if your calculation comes up with 250, then you're going to get an overflow.
Yes. Right? Can everybody get that? So, for example, for 8 bits, how many possible combinations? What if you're unsigned integer? What is the range you can represent? 65, right? But what if you add 2 numbers? Both are 8-bit numbers. Let's say 200 and 100. What's the result? 300. Can you represent 300 with an 8-bit value, unsigned integer? What do you think the computer will display, will return, if you add 200 with 100?
Random.
Not random. It's deterministic. But what?
The overflow should be 5 plus the difference was 200.
Yes. Correct. I hope it's not random, right? It could be random. That's why we have error checking, and there may be cosmic ray hitting your chip in a certain way that flips some bits. But in this case, conceptually, it just rolls over. Will the computer let you know if this happens? Yes/no. Depends. Some computers do, some computers don't. Usually, like in microcontrollers, they have the carry flag that you can use to see if you have carry out on your unsigned integer. PLP doesn't have it. So with the PLP CPU we use, it's all up to you to figure out whether there's an overflow. So you have to do it in software. Does that make sense? It's because the philosophy of the PLP CPU is to keep it simple. Right? If you can do it in software, you should. Because if you take co-part with me, well, with my advisor, the next step in this series, in CBS, you learn how to program it. In computer architecture, what do you think you'll do? Create, design, and create PLP CPU. Right? So you're able to program it, and then you design to support the programs. Well, that's if you take co-part. So, if it doesn't, how do you handle this problem of overflow? Logic. There is some logic into it that you can see, hey, this answer does not make any sense, and you have to figure out what happened. Cool? Any question? No? No, Neo. It's up to you. All right. So, like I said before, so you have 8 bits, 63, 200. You add them together, you have 263. It cannot be represented by an 8-bit unsigned integer. That's an error, overflow. Well, that's an exception, not error. But if left unhandled in some program, what do you think will happen? Remember that civilization game example in the lab I told you about? Did I tell us in the class or in the lab? So if you haven't heard, it's like in the game, so the AI has this variable that represents the tendency of that AI to nuke you, right? So Gandhi is a pacifist, right? So this value for Gandhi is really low, 1. Right, makes sense. So he barely nukes anybody, unless his civilization takes democracy. So when you switch to democracy in civilization, it reduces the AI's tendency to be aggressive, right? So it reduces that variable by 2. So Gandhi already has 1 on his variable. What happens when you subtract 2 from it? It rolls over to 255. Now he's super aggressive. Right, so if you play Civilization 2, that's where you started, and you have Gandhi as your opponent, and if he takes democracy, cross your fingers, because he may be next. That was a bug, right? It's just a game, it's okay. But what do you think if it happens on something else, something really critical? So make sure that you deal with your possible overflows. Cool? Any question? All right. So if it's unsigned, pretty simple. If you have a carryout, then you have an overflow. Keep in mind, carryout does not equal overflow. Carry is just an arithmetic concept where your answer requires an additional digit. Just like when you decimal. 9 plus 7 is 6 with 1, the next digit. That's carry. It's an arithmetic concept. But in unsigned operation, you can use it to detect overflow, because some microcontrollers have the carry flag, right? So you can use that bit to say, hey, I have a carry being set. That means the previous addition is could be an overflow, depending on your context. Where do you think you can use the carry bit for something else? Let's say your CPU is 8 bits, and you want to add 2 16-bits numbers together. Does that make sense? So you take the bottom 8, add them together. If you have a carry, then you carry it to the next 8 bits additions. That's why you have the carry bit for additions in microcontrollers. So you can chain them together and add bigger numbers bigger than what your CPU width is. Cool? So 200 plus 60 is definitely not 7. It's definitely wrong, so you have to handle this. For 2's complement, when you add two numbers with different signs, can you get overflow? Impossible, because the resulting value will be smaller, right? If the signs are different, you cannot have sign overflow. If they are the same, but the sign is also the same, the result have the same sign, then you don't have overflow. Does that make sense? Now, if your operands have the same sign and the result has different sign, it has to be overflow. If you add 2 negative numbers together, can you have a positive number result? Impossible. That means your answer is wrong. So this is actually how CPU designs detect sign overflow. In the Motorola, it's the V flag, if you use the Motorola. So some recap. Modern computers are digital. So that means that it's best represented in binary. Data values, bit length, and its implications. Binary arithmetic, signed integer, Overflows? Any questions so far? Overwhelming? Underwhelming? Just right? Lukewarm? But you understand the reason why we're doing these topics. That's more important. Why binary? Right? Yes, no? Why?
No, I said I don't understand
Why
why.
we learn this?
Well, I mean, I assume for the PLP, but
No. PLP is just a vehicle, a tool to learn all these concepts. What I'm asking is, why do we learn these specific concepts?
when we have a mistake, we can try and fix it.
For overflow, yes. How about bit length? Why is bit length important?
Conservation of memory.
Conservation of memory, that's a good concept, good idea. You don't want to allocate more than you need. So all these topics will carry over all through the semester and the rest of your life if you deal with computers, right? How does computer do arithmetic? It's important because it's 90% of the time that's what it does. Even your desktop does a lot of calculation all the time. Just idling, it does a lot of computation. Cool? Now, is arithmetic the only operations that you do? No, of course not. So you can have logical operations. So basically, sometimes when you program a controller or CPU, you just need to do some logical operations. Like what? Give an example. What's a logical operation? That's arithmetic. Yeah.
Switch if like an if statement, turn one of the big
Compare.
Compare.
That's a bit like arithmetic too, because you just subtract to see if the result is 0, right? To see if something is equal or less or whatever.
Just on a modern computer, just displaying the image, a JPEG or something, isn't it just pulling data out and displaying it, not actually doing
That's
it?
data transfer. In the CPU itself, other than arithmetic, what can you do? Logical. What are logical operations?
Switch statement.
How do you check for things? Compare. But sometimes you just want to check certain part of a number. Remember ANDing, ORing, XORing? That's what kind of operation that other kind of operation that the CPU does. So basically, you're given a number, and then you give another number and do each logical operation per bit. Because some of these values are not numbers. They may represent LEDs, right? Like in the lab, when you use an IoT device, it could be LEDs or switches. Let's say you have 8 switches, but you're only interested in the second switch. Then logical operation comes in. Hey, we can AND this number with zeros except for that 1 bit to get that value. You will do this a lot when you program microcontrollers to program whatever, your toaster or whatever in here. So it's important to know that computers can do logical operations. Any question? For example, let's say you have this 8-bit value, 00001111. You AND it with this value, right? This is bitwise operation, not like arithmetic. For example, for this first 4 bits, you have all zeros. What 0 ended with 1? 0. 0 ended with 1? 0. So all this becomes 0, right? As you see here. And this part, it's all 1s, and you end it with this part. So only where both locations are 1 would you get a 1. That's logical operations. You'll see this more as we go through the class and see where this is used. Cool? But you get the basic idea how bitwise operation works and how they are different than arithmetic operation. Cool. And this is OR. So basically, if you have something with a 1, you get a 1, right? If you need to review logic gates, please let me know. I can spend a lecture on this.
what is the basic definition of this logic operation, and what would you? It's kind of lost on, I guess.
So we've been talking about numbers, but sometimes your data is not a number. It's just a bunch of bits representing something. Like in the lab, it could be representing the state of the switches. It could represent the states of the LEDs, right? In that case, sometimes arithmetic operation doesn't make sense at all, right? And you want to mask off things, and you just interested in some value, so you just end it, or you'll see later. But I just want to know that that this exists. This kind of operation exists, because this will be a pain to implement if you just have arithmetic operations, right? XOR. So with a simple CPU, now we learn that the registers can have limited bit length. So depending on the CPU design. Also the ALU. So how the CPU data path width, like how wide they are, will affect how you program the CPU. And how wide your address bus determines how many spots in memory you can access, which we'll see later. So is number the only thing that you want to represent? No. Sometimes you want to represent text, human-readable text. So one way to do it is with ASCII. Okay, so it's an 8-bit representation of a character. Simple enough? So this is like a really old table of what ASCII is. For example, if you want to encode the letter A, so the first nibble is 4, and second nibble is 2. Right? No, 41, yeah. 41 hex is A. So it's up to the programmer to determine whether it's ASCII character, or is it just a number, or is it just like a combination of bits. That's the main idea I want you to be aware of. To the computers, they're just numbers. There's values. You ascribe meaning to it. Is this 1 byte a character? Or is this 1 byte an unsigned integer? Is this 1 byte 2's complement? Or is this 1 byte just a bunch of bits that I need to store some state of something? Is that clear? That's the whole point of this lecture. The computers do not care. It's just a bunch of bits. You ascribe meaning to it. Cool? Any question? Computers are really cold. It does not care. All right. Yada, yada, yada. So I guess right after this, we'll talk about memory and I/O, the PLP CPU, and let's open the next lecture. Oops. Yeah, we just went. All right, memory. Cool stuff. Why do we need memory, first of all? What is memory?
Temporary hardware storage, not cache.
Temporary storage. I said memory, not the picture is misleading, but memory could be a lot of things. Because register is also memory. Right?
Faster.
Huh?
Faster.
Much faster. Very, very fast.
Registers cache, or those two the same?
No, they are not the same.
So the register is on the ALU.
No, you'll see. All right, so memory and I/O, instruction encoding with the PLP CPU. Okay, memory. So Charles, right? As he said, there are different kinds of memory. We've seen registers. Where are the registers? Not on the ALU, but on the CPU itself. So really, really close to the processing center of the computer. Why do you think it's there? Speed, because the CPU is very, very fast. So when it wants to do operations, it wants its data to be close, right? So memory usually is location address, index value. You give it an index, it returns a value, right? Or if you give both index and value and tell it to write to it, it'll write to that location. Most memory is byte addressable. What does it mean by byte addressable, do you think? So each address points to a what? Yes, exactly. So each byte value gets assigned an address, right? So an address is basically just a number included as binary. So it's just signals that go into the memory to tell it what to get or where to get it or where to put your data. Cool? So you've heard this, right? ROM, RAM. What's the difference? Why do you ever need a read-only memory?
System instructions.
Program that you will never ever have to change again, or values, constants that you just need once. Yeah, like my bike computer, right? I have my program on the ROM, and I have my information of my wheel on the ROM because you never need to change it, right? Firmware for your microwave, hopefully in the ROM. You don't want somebody to call you in and say, hey, we need to patch your microwave. What? What was wrong with it? Why does my microwave need an access to internet?
Have you seen that website, downloadram.com?
Yes. So that's in terms of whether something is writable or not, right? Random access memory is kind of a bit of like
Didn't they change the name from random?
whatever.
Something else now? It's not random.
Because most ROM is also random access. Right,
So with RAM, you got a system with, I don't know, 8 gigs of RAM. Every 8-bit segment has a unique address of that 8 gigabytes. That's a lot of addresses.
what's the smallest data type that you have ever used in Java or C? Boolean? How many bits do you think a Boolean occupy? 8 bits. Usually 8 bits, but some compilers optimize. No, it's just it takes the whole 8 bits. But some compilers optimize where you can fit 8 Boolean variables in a single byte. But on general purpose computer, it's worthless. You just spend more time trying to isolate each bit, right? In a microcontroller, when you have only 48 bytes of RAM and a few kilobytes of program memory, it makes sense to pack all your booleans to like 1 byte.
What I'm asking is, if you've got 8 billion bits divided by 8 bytes, that's a billion bytes of data. And so, by necessity, one of those things has an address that's got to represent a billion. I mean, if the address of this block is 1, the address of this block is a billion.
Yes.
So it's got to be like a lot of data used up just for addresses.
No, because address is used just one at a time. You just spit out an address, and it'll give you the data.
But how does it know if it says to go to block 1 billion? It goes to the RAM, and there's a huge array of
That's why
data.
RAM has a controller. So if you take VLSI or other senior level courses that deal with this, you actually design memory controllers. We can talk about it later in the semester, like how memory works. It's actually pretty neat. If you take digital logic, you've learned flip-flops, right? Some registers are made with flip-flops. The thing with flip-flops, they are huge, right? They're fast, but flip-flops are very fast, but they're expensive. It takes about tens of transistors. Dynamic RAM that you use for main memory only has few transistors, 2, I think. So that you can pack more memory. That's why you only have 32 registers on the CPU, for example. And you have cache that has few megabytes, and then you have gazillion gigabytes for your RAM, and then you have trillion gigabytes for your disk.
There's so much megabytes of RAM. It seems like there's individual chips on it, so I bet they don't go all the way to the billions, probably maybe thousands for each chip.
Sorry, it could be a billion per
I've
chip.
got my micro SD card in my tablet that's 64 gig, and it's smaller than you think.
Yes, it's more packed, but it's slower than RAM, right?
Right.
So it's a trade-off. So You can't pack 8 gigs of storage on your CPU. There's just no space. Right? Trust me, like if they can, they would. So usually on the CPU die, they're packed with cache slots. So when I intern in Intel, they say like, we can add features, right? But it's a trade-off, because the more you add features into the die, you take space from having fast memory on the chip, right? So it's a very expensive real estate to put things on the die. Yes.
I was told they were deciding the speed of the processors, that they would get the chip, and then they would speed test it, and then they're getting a higher frequency processor. That's just a better quality chip.
Yes, it's called binning, right? So you produce a bunch of chips, and they test it. Things that pass the more stringent test becomes the higher that sell more, right? And the idea is that you make sure like it matches with your expectation of what you can sell.
So slow paying, we call cell runs.
Yeah, that's why they disabled some of the caches, because probably there were some defects on the chip that they can still sell it. They just don't throw it away, but it just down market. Like, hey, this is cheaper version. Any question?
Can you explain a little bit better where a register is if it's not on the CPU itself? Is it on the bus of the CPU?
You'll see.
ALU.
It's not on the ALU. ALU and
The
register.
register feeds into the ALU, right?
Yeah, it's connected to the ALU on the chip.
And it's on the bus, but not, because I said earlier.
No, bus doesn't have anything to do with registers and ALU. It's internal to the CPU. Bus is what you use to interface with the CPU outside.
I meant the board of the chips. Yes.
It's routing, like wires, just a bunch of wires inside each. I'm not even calling wires, it's like this little plating or whatever. Okay, so memory. So this is the structure of memory. You have address, and then associated with each address is a byte of value. And outside, you have the port, and you have the bus. You have the address bus, n bits. Depending on how many wires you have on this bus, you can address more on the memory. And you have the data bus that carries the actual value. And you have the control that tells the memory, hey, I'm reading or writing. Make sense? In the real world, people who design this port is probably a team of engineers just designing the port. It's on its own world right here. Like if you work with desktop computers, what's DDR, what's DDR2, what's DDR3? It's like, well, how does it work? How do you pump more and more data into it? It's crazy. Right? So let's say we want to write a value to some location here. So let's say we want to write to location number 4, address 4. So on the bus, we drive the number 4 on the address bus. We drive the data bus with the value we want, and we tell the memory to write. There is some timing consideration. Right? So if you want to interface with RAM, like if you work in a microcontroller, hey, I need 64K RAM on my chip, on the board. You will have to learn about how to time it and everything. But as engineers, you can learn this in a weekend, right? But in high-level concept, this is what you'll have to do. The intricacies, you learn about it later in your career. Or you may be a computer architect and you actually design the memory. Right? Okay, now we have the value stored in that address. How do you retrieve a value? Just give an address and then tell it, hey, I'm reading. And then the memory will drive the data bus. Right. So can you write and read at the same time?
Yes, but it's slow.
Wait, you cannot. You physically cannot do that with just one bus. But with 2 buses, then the memory has to have an extra port. Right, so. Who's in computer engineering? So you guys will deal with that. So you have to take VLSI, right? You guys have to invest more in your career choice. All right. So, deeper questions. Yeah. What if your word is not 1 byte? Keep in mind, the questions Neo is asking is what I might ask in tests. And if you haven't noticed, Golem is gone.
Fragmentation.
Well, no, that's the idea of having a multi-byte word. So you don't have that, right? Yeah. So just yeah, but what if your word's not 1 byte and you have byte addressable memory? Right? How about PLP? I've been saying that PLP is 32 bits. How do these 32 bits get encoded, and how is it stored? What if you want to get instructions and data at the same time? I said this before. What do you do? No, same time. Concatenate means you do it after. I just told you guys. 2 buses, right? What's the disadvantage of having 2 buses?
What's the advantage of not having 2 buses? You can do 2 things at once, I guess.
Disadvantage, sorry.
Oh.
It's faster, hopefully. More space. Keep in mind, if you're a 32-bit system, the address bus is 32 bits. That's 32 wires. When I say wires, it are traces on your PC board.
What's a 2-inch motor?
Huh?
What's a 2-inch motor?
Seriously. Well, if on a modern CPU, you don't even see that. It's inside the memory controller is inside the CPU.
You generate more heat too, wouldn't it?
Yes. More signals to switch, more energy you consume. Right? So this is how PLP instructions encoded. So there are 3 types. I'll talk about the first 2. The first one is register instructions. What did I say about register instructions? What's the defining characteristic of an R-type instruction? They do operations on what? On registers, right? So you give it 2 source registers, CPU will pull them off, and then tell the LE to do work, and store it back to the 3rd register. Does it make sense? So as you can see, you have all these fields, and you cannot fit a 32-bit number. Right? That's why we have to split LUI and ORI to load a 32-bit number to the CPU, like you saw before. And LUI and ORI is I-type, where you have a 16-bit immediate field where you can have a solid number that you can just load it. Does it make sense? Question? So this is how PLP instruction encoded in binary. So the opcode tells the CPU what to do. The RS, RT, and RD are the register fields, tells the CPU which registers to use. On the R-type, the shift AMT, shift amount field, tells the shift instructions how many bit places you're shifting. You'll see later. And on the R-type, the function tells the CPU what to do. Adding, subtracting, multiplying, whatever. Cool? So let's see how PLP instructions look in binary. You've seen PLP tool, right? In the lab. Let's put some instruction. Let's load the upper and load the lower and add them together and start. All right. Oh, let's get load the second number. You see that? So this is still human readable. Do you agree? That's why you have assembly language. So the first instruction is just, hey, load this value to the upper field of this register. We cannot load a 32-bit number straight because it doesn't fit, because the instruction itself is 32-bit. If the whole thing is a number, is a value, how does the CPU know what to do? That's why we have the opcode and the register fields. All microcontrollers, CPUs have something like this, like how to address a register, what to do, what to load. So opcode, register fields, operands, they are common in all computing systems. So now let's see how it looks in binary. So we assemble this. Oops, sorry. Messy. So this is what actually gets stored. Stop resizing. Okay. So these are the 5 instructions we just wrote. All right. So this is LUI1 feed. You can see this feed there. It's been encoded in the bottom 16 bits. And you see beef here, 0 foof. And here is the opcode and the register fields being encoded. Does that make sense? So it's just a number. And the LU doesn't really make any sense because it's just a bunch of bit combinations. But the point is, instructions are just what? Some bit combination. We use assembly language because we don't want to type the program in that way. Can you imagine? Hey, how to add 0, 3, 4, 2, foof. How to subtract 3, 4, 4, A, B, C, D, D, E. It's like, are you kidding me? That's why we have assembly language, right? At least it's still human readable, but still close enough to the hardware that you know it will be get executed just like that. But in C program, Java program, the interface is still, it's far removed. So the structure of a C program does not really show how the CPU will execute. Does that make sense? Well, it shows some flow, but not like what registers are the CPU going to use, how it's going to access memory, where it's going to put this variable, things like that. It doesn't show. In assembly, that's still obvious. Does it make sense? Cool. So all the instructions are 32-bit values. Now let's look at the big picture. So this is, now you finally see a PLP CPU connected to a 16 megabyte main memory. So the new things here are the program counter. So the program counter is hooked up to the address bus of the first memory port. What do you think program counter does? Counts programs. That's where the name came from. But physically here, what is its function? What is it its function? What is it its function? It asks the memory for the next instruction to execute. Does that make sense? So in CPUs, program counter always has the address of the next instruction to execute. That's what it's for. The instruction register holds the actual value of the instruction that is being executed. So the CPU takes whatever is in IR, decodes it, I have to do this, and then do the rest of the execution. Does that make sense? And then you have the 32 registers that are not in the ALU there. Right? So in PLP, there are 32 registers, where the first register is 0 register. That's always returns 0, no matter what you do with it. Cool?
When you keep referencing PLP, you're talking about the software where you're using.
The architecture.
Okay. Is it? Are we sort of simulating talking to a microcontroller? That's
I will bring a physical board where it's implemented. In the software, it's being simulated.
Right. So that's what we're doing in there.
Yes.
We're
You're programming a CPU.
And we've got the switches and the LEDs hooked up.
Next week I'll bring the actual board where you can see the switches and everything.
So PLP is it an architecture or is this piece of software?
PLP is the project. PLP CPU is the architecture. PLP tool is the software you use, the tool you use to actually learn the concepts.
So we'll be using the same interface to actually control the physical board.
Yes.
We want to do also. That's cool.
Instead of simulate, you just hit program. Right? The duct tape is assembles, and you have the monitor for simulating, you have the serial port program. Any question? PLP CPU is MIPS based. So if you actually use MIPS later, you'll see it's pretty similar. But not all architectures are like this. Like I said before, like I said in the first class, it's just a tool to convey the concepts. Because PLP CPU is not used in the industry, but it's irrelevant.
You guys came up with?
Yes.
Very cool.
Based on
I mean,
MIPS.
my buddies that have taken PBS before, they horror stories about the Texas or whatever.
Yeah, Texas is a Motorola 6811 simulator.
Right.
Yeah. The thing with Motorola is there's some idiosyncrasies that just make it hard to learn some concepts. And we try to remove all that. If you go to automotive industry, you may see Motorola's. They still use them. Like if you work for Ford or GM. So it depends on where you work. Quick microcontrollers are big. If you work in electronics like cell phones, you will see ARM architecture. See, it's pointless to teach you like a single architecture in this class. It's not an ARM class. It's not a Motorola class. It's a computer-based systems classes. Please keep this in mind. Cool? So I'm not teaching you useless stuff. This is actually pretty cool. Said the instructor. So you have two buses. So the first one is instruction bus, and second is the bus. So is this von Neumann or is it Harvard architecture? No, it's actually, you only have one memory. It's von Neumann, right? Program and other shared memory. It's just that we have two buses to work around the von Neumann bottleneck, where program and other have to wait for each other. But the disadvantage is now you have 80 more wires to the system that connect the memory with the CPU. So what's inside that 16 megabytes main memory? Bunch of rows. That's basically what it is. Each addressed uniquely. So in PLP, the main memory is addressed from 10000 to 10 whatever. Right, 16 megabytes. Yes.
The 0 at the very beginning for the X is eventually going to go 1 as that block memory.
Say it again.
That 0 at the very beginning will eventually turn into a 1.
I don't get you.
Turns it always to 0.
No, 0x just denotes it's hexadecimal.
Oh.
Yeah. Otherwise, it could be confusing. Is it 10 billion or whatever? It's hexadecimal 100. This is the case where the value doesn't matter. It's just a combination of bits, right, to have an address. So you may be asking me, why does the address skip from 0 to 4? Who can answer this? Raymond.
I'm not going to, but I just want you to know that I could.
Oh,
Because there's
Wow.
4 bytes.
Yes. And 4 bytes because?
30 minutes.
Yes, because the word in the CPU is 32 bits. Does they already get that? Is the memory still byte addressable? Yes, that's the whole reason why you jump the 4 bits, the jump 4s. The CPU, however, since it's a 32-bit system, only access in 4 bytes.
Okay, so if it was 64,
Yes. The address bus would be 64 bits, and the data will be 64.
Because this is 32-bit, this particular architecture, the addresses are 4
Yeah.
bytes.
It doesn't make sense to get each byte because the CPU works with 4 byte blocks. Cool? So it's still byte addressable. So the first one is actually 10000000010003. But if you in PLP CPU, if you tell it to hey load address 03, you know what it does? It just chops off the bottom 2 bits and just get you the whole 4 bits, the whole 4 bytes. So you can't do byte load. On the MIPS, you can. It does some magic that actually lets you get this 1 byte. But to do that, you add extra hardware. Our philosophy, just let the programmer do it. Cool. This is just an aside. You don't really need to know like what endian is, but A big endian just means the most significant byte comes in the lower address. Right? PLP CPU is this like this, MIPS is like this. Little endian is where the most significant byte comes last. So it's the least significant byte first. On a single computer, it doesn't really make sense. It doesn't really come into play, right, in a PLP CPU because everything is 32 bits. But when you start trying to network or make two computers with different endianness talk to each other, then it could be a problem. So unless you work in low-level networking stuff, yes?
What do you mean about more significant bytes? Like say, like read it right to left versus
Left to right. From left to right.
Right.
Think of it in terms of decimal. 763. Which one is the most significant digit?
Right, that's what I'm saying.
Yes.
So an analogy is reading left to right or right to left when you're talking about the significance.
Yeah, an example would be, let's say you want to transmit the word John. Each character is a byte, for example, right, as ASCII. So it's encoded in one word. PLP sends N first, right, John, N-H-O-J. If the receiving computer is little endian, you say, oh, you just send me N Hodge. That could be messy, right? That's why the two ends have to make sure that they are speaking the same endianness. So unless you work on a low-level networking stuff, I don't think you'll ever see this in any meaningful capacity. But it's nice to know that this thing exists because people were just being arbitrary back in the days. Some people design a CPU, oh, let's make it this way. Some people design that CPU, oh, let's make it this way.
And they still do that today? Some
Yeah.
people make stuff.
Intel is little endian. ARM is big endian. So when they try to come together and communicate, oh,
You think they should get together on that?
No. Ponder on that. How often can we as humans come together? Like
That begs the question: what does Apple do?
Apple uses Intel,
Okay.
right? So
they don't have their own. They're the lowest they go is they route through Intel.
yeah, and even their OS is Unix, right? Now, when you boot up the computer, it has a reset vector where it starts executing from that address. So it loads the PC with that address. Some controllers, it's 0. In PLP CPU, it's 1000. So it points to the first word of the memory. So how do you program the controller? So you have memory where you store the program and data. So how do you think you program it? On the finished product, it's flashed, right? So let's say you have a microwave and you have millions of control boards. You don't want to program it manually, right? So you just flash each chip and then produce it. And don't touch it ever again, right? But when you're prototyping and debugging, you have some programmers that just hook it to the board and start flashing the. Have you ever rooted your phone? It's basically what you're doing, right? You're flashing the firmware of your phone. Or if you're using a laptop, basically you have this thing called operating systems where you can just program in C, compile, store it on disk. So there are other programs that work for you that allow you to launch your programs, execute your programs. There's some indirection there. Any question? Because you might ask, how did the program get into memory? Right? So there are 3 things that may have happened before you run it. And then reset vector will make the CPU execute starting from that address. Now, let's program our CPU. So now we have our addresses, our instructions on main memory. Right? So I put the assembly language, not the hex for legibility, so it's legible. Let's finish it up and we wrap it up. So this is similar to the program you saw in the lab. What do you think the 2 instructions do? You're loading this number to which register? 1. What do you think that number is? 100024 is what? Is the address to this bit of data. Remember? You have to actually load the address first before you can actually access the data. Let's step through this program. So first, before you cycle, the PC points at this, the reset vector, right? So the first cycle, that instruction gets loaded to your IR, and then gets executed. And the end result of this instruction is that this gets loaded to your register. Does it make sense? So the next one will be this. Notice that the data bus is idle because you're not using it. You're just fetching programs from memory with this instruction bus. That's what immediate instructions do. Right? But you don't really need anything from your memory for data. So this is idle. So after this instruction, then you have the address in register 1. Next, what is this? Now you have load word. As you saw in the lab, what does load word do?
Load the two with the information.
Correct, right? So 1 has the address. So now the data bus gets used. Both gets used. If you only have one bus, it has to wait until the instruction gets fetched. Right, the next gets fetched. Here you can do it in the same time. So it saves time. Hey, what's in 1? Okay, this. So you put that value in the address bus, and the memory will go, okay, I'll get you this value, and you tell it to read it. Boom, it gets put here. Now, what you didn't see last Thursday, this 4, right? At 4. Since we know that the variables are next to each other, we use this facility. Hey, use the address in here, but add 4 to it, so I access the next one. That's why we have that field on load word and store word. So you have a base address, and you can just offset into whatever you need. Cool? Now, you have whatever is in this address in this register. The value gets loaded to this register. Now you add them together. So this plus this, you get FF. So in this instruction is R type. So you don't have immediate. You just use all the registers, fields. So the data bus will be idle. You take the value from register 2, take the value from register 3, add them together. The LU does it, and store it back in register 2. Cool? Now we want to put it back, so we have a store word so we take this address, 0 offset, then the data bus gets used again, but this time it's been written to, and then the value from here gets stored out here. Any question? So now, before on the simple CPU, you have some sense of program execution, but there's no sense of bit length, right? There's no sense of buses. There's no sense of immediate values. But now you can see clearly the different concepts and the different abstractions that happen underneath. Cool? And this is common to a lot of microcontrollers. Like the general concepts of accessing memory, what do the buses use for? What are the buses used for? And the registers, things like that. Any question? Yes?
The setup you have, I mean, that's pretty basic for any CPU and knowing that.
Yeah.
Just how a bus would work.
Well, there are intricacies, right? Like I said before, the timing of it could be really complex. But from higher level, this is basically it. This is what the CPU does. Any question? I don't want to get into I/O yet because we're out of time. Good? All right, I'll see you Wednesday.
Can you define clearly?
The what?
You keep saying I can see stuff clearly. I think your definition of my definition clearly.
Like what?